The information available regarding Graham Stetzer filters and their claimed benefits for power quality and health suggests caution is warranted. While the study mentions improvements in power quality and reductions in various health conditions, the supporting independent scientific evidence is limited. The provided case studies and articles from the Cancer Society offer anecdotal evidence, but these alone are insufficient to establish a causal relationship between the filters and the reported effects. When evaluating the potential use of Graham Stetzer filters for improving power quality and potentially impacting health, several benefits and concerns should be considered. A potential benefit is reduced electrical noise. Filters may reduce electrical noise, which could lead to improved performance of electronic devices and a potential reduction in electromagnetic interference or EMI. Improved air quality is another possible benefit. Some studies suggest filters might remove particulate matter and allergens from the air. However, it is important to address the concerns. Firstly, there is limited evidence. As noted previously, the scientific evidence supporting the health claims made by the filter manufacturer is limited. Secondly, the cost of installing and maintaining Graham Stetzer filters can be significant. Thirdly, the long-term health effects of using these filters are currently unknown. Based on the currently available information, drawing a definitive conclusion about the effectiveness of Graham Stetzer filters in reducing health conditions is difficult. Further, independent scientific research is necessary to determine the validity of the claims made. It is recommended to approach the use of Graham Stetzer filters with caution until more evidence is available. The potential benefits should be carefully weighed against the potential costs and concerns before deciding on their use. Electrical noise, also known as electromagnetic interference or EMI, is unwanted electrical signals that can disrupt the operation of electronic devices. Sources of electrical noise can be both internal and external to a system. Internal sources include switching power supplies, digital circuits, and electric motors. External sources include radio transmitters, power lines, and lightning. Electromagnetic interference can manifest in various ways, such as static on a radio, distortion in audio equipment, or glitches in computer systems. In severe cases, it can cause equipment malfunction or failure. Power quality refers to the characteristics of electrical power at a given point in an electrical system, evaluated against a set of reference technical parameters. Good power quality means that the voltage, current, and frequency are within acceptable limits and that the waveform is sinusoidal. Poor power quality can lead to a variety of problems, including equipment malfunction, premature equipment failure, increased energy costs, and data loss. Common power quality problems include voltage sags, voltage swells, harmonics, and transients. Electromagnetic fields or EMF are invisible areas of energy, often referred to as radiation, that are produced by electricity. EMF are typically grouped into two categories: low frequency, also known as non-ionizing radiation, and high frequency, also known as ionizing radiation. Low frequency EMF are produced by power lines, electrical wiring, and electrical appliances. High frequency EMF are produced by radio waves, microwaves, and X-rays. Some people are concerned about the potential health effects of exposure to EMF. However, the scientific evidence on this topic is mixed. Some studies have suggested that exposure to high levels of EMF may be associated with an increased risk of cancer, while other studies have found no such association. More research is needed to determine the long-term health effects of exposure to EMF. If you are concerned about exposure to EMF, there are a few things you can do to reduce your exposure. These include increasing your distance from EMF sources, limiting your time spent near EMF sources, and using shielding materials to block EMF. Air quality refers to the degree to which the ambient air is free from pollution. Air pollution can come from a variety of sources, including industrial emissions, vehicle exhaust, and wildfires. Air pollution can have a number of negative effects on human health, including respiratory problems, cardiovascular disease, and cancer. There are a number of things that can be done to improve air quality. These include reducing emissions from industrial sources, promoting the use of public transportation and electric vehicles, and planting trees. Electrical wiring, covered by the National Electrical Code, or NEC, must adhere to certain standards to ensure safety and proper operation. Article 310 of the NEC covers conductors for general wiring. It specifies requirements for conductor insulation, ampacity, and installation. Ampacity is the current carrying capacity of a conductor expressed in amps. It is determined by the conductor's size, material, insulation type, and insulation conditions. NEC Table 310.15b16 provides ampacity ratings for various conductor types based on their size and insulation temperature rating. For example, a 12 American wire gauge or AWG copper conductor with THHN insulation rated for 90 degrees Celsius has an ampacity of 30 amps in certain conditions. However, this ampacity must be adjusted for ambient temperature and the number of conductors in a raceway. If the ambient temperature exceeds 30 degrees Celsius, the ampacity must be reduced using correction factors found in NEC Table 310.15b2. Similarly, if there are more than 3 current-carrying conductors in a raceway, the ampacity must be derated using adjustment factors in NEC Table 310.15 cone. For example, if there are 6 current-carrying conductors in a raceway, the ampacity must be derated to 80% of its original value. This derating is necessary to prevent the conductors from overheating and potentially causing a fire. Proper grounding and bonding are critical for electrical safety. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices such as circuit breakers or fuses to trip and clear the fault. Bonding ensures that all metal parts of an electrical system are at the same electrical potential, minimizing the risk of electric shock. NEC Article 250 covers grounding and bonding requirements. It specifies the size and type of grounding and bonding conductors, as well as the methods for connecting them. For example, the size of the grounding electrode conductor for a service entrance depends on the size of the service entrance conductors. NEC Table 250.66 provides the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Proper overcurrent protection is essential to prevent damage to electrical equipment and to protect against electrical fires. Overcurrent protective devices such as circuit breakers and fuses are designed to interrupt the flow of current when it exceeds a safe level. NEC Article 240 covers overcurrent protection requirements. It specifies the types and sizes of overcurrent protective devices that are permitted for different applications. For example, the maximum size of a circuit breaker or fuse for a branch circuit is typically determined by the ampacity of the conductors in the circuit. NEC Table 240.4b provides the standard ampere ratings for fuses and circuit breakers. Electrical safety is of paramount importance. Working on electrical systems can be dangerous if proper precautions are not taken. Always to energize circuits before working on them and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not qualified to work on electrical systems, hire a qualified electrician.